Here's lesson 3-5, but first let's remember 3-4. You learned the triangle sum theorem, which is that interior angles of a triangle add up to 180. You also learned the triangle exterior angle theorem, which says that an exterior angle, right over there, is equal to the sum of the two remote interiors. So those green ones that I've noted here and here. So once you know this, then these two green ones will add up to, let me put a little plus symbol there, will add up to be the measurement of that red one. Okay, now that we know that about triangles, let's move on to other polygons. Poly means many, gon means side, so many-sided things. Now, Polygon AngleSum theorem. Wait a minute, didn't we just learn the triangle sum theorem? Yes, we did. So here is a new thing that will apply to any polygon ever, including triangles. So the sum of the measures of the angles of an n-gon. What on earth is an n-gon? Well, stick with me for just a second. We've got a formula, a very useful formula, one that should be stuck in your brain from now until you get Alzheimer's when you're 80. So the sum of the measures of the angles of a whatever this is, here's the deal. N-gon means, pick a number. And whatever number you just picked, put that in for the n. So if you wanted a 27-sided figure, then 27 is your n. So we call this a 27-gon. There's some much catchier names for numbers that are lower than this, like hexagon. How many sides does a hexagon have? It has 6 sides. Gon is the word for sides. Yes, you could call it a 6-gon, but people would look at you funny. And if that's a motivation, then don't call it a 6-gon, call it a hexagon. You should maybe remember some of the other Greek names that we use. I'll write them out right here for your benefit. 4-sided is a quadrilateral. 5-sided is pentagon. 6-sided, hexagon, got it. Do you know what 7 would be? 7 is a heptagon. We don't hear that much. 8, yep, octagon. 9, I think, is the funnest one to say. Nonagon. 10, decagon. I'm going to skip over 11 and go to 12. Decagon. Do you see what they did there? Do for 2, deca for 10. So it's adding up. 2 plus 10 makes a decagon, or a 12-sided figure. Great. Now, let's continue. We have the sum of the measures of the angles in a whatever number-sided figure you want is, pick that number, subtract 2, multiply it by 180. Does that work for triangles? Hey, how many sides does a triangle have? 3. Whoa. Sorry. 3 sides on the triangle. And 3, take away 2, that's 1. 1 times 180 is exactly what the triangle sum theorem said. Now, do you know that a quadrilateral, or squares or rectangles, those interior angles add up to 360? Well, you knew that, but does it work in this formula? Let's see, 4, make that your n. Take away 2, that's 2. 2 times 180, 360. Got it. And so the pattern goes. So, always remember, n minus 2 times 180. So that was the interior angles. Interior. And just like we had up here, we've got some interior angles, and now we're going to talk about some exterior angles. So this exterior angle theorem for polygons is a little different than the triangle thing. We're not going to be trying to figure out use the remote interiors. We're just going to care about all of the exterior angles. Now, exterior angles, you can see in the diagram here, are the angles that are made by the sides getting extended. Now, you're only extending one of the sides, aren't you? Let me go this way. If I start here and move up, oop, that's not green. There's green. Try again. There we go. So I've only extended this line at one of those moments. Not in both making an X. We don't need an X. We just need to extend one side at a time. So this is the amazing fact. If you add up the measure of every one of these exterior angles, you will always get 360 degrees. Amazing. Now, does that work for a dodecagon? Yes. Yes, it does. Oops. So, when you add them all up, they add to 360. We'll prove that another day. Now, here is the definition, and I've copied it from the teacher's manual because I can't write that small and fit it all on one line. So, pause the video and copy that down. Okay, now let's talk about polygons. Hey, there's a polygon. How many sides does it have? 5. So it would be called a pentagon. Now, is this a polygon? Nope. Why? Well, it's not a polygon because it's not a closed figure. So we're missing the connection between A and E. Then, is this a polygon? Nope. How come? Because we have two sides that intersect between endpoints. So the side A to E intersects the side from C to D, and we can't do that. That's not a 5-sided figure. We have two smaller figures now, don't we? Yes, but we're not talking about that. We're talking about the whole thing. So the whole thing, not a polygon. Now, convex and concave. Here are your definitions. Convex polygon does not have diagonal points outside of the polygon. Diagonal points? What? If you connect the corners of your polygon and not going along one side, but skip one of the endpoints and go to the next one, you see the dotted lines in here. Those are diagonals. Diagonals don't have to only be on squares. You can have diagonals in a pentagon, in an octagon, in a dodecagon, in a 27gon. There are diagonals there. Lots of fun patterns with diagonals in those figures as well. So, as long as the diagonals are inside the figure, you're good. It's a convex polygon. So the definition is sort of a negative version. Convex polygon doesn't have diagonals outside, which means it does have diagonals inside. Inside. So this is a convex polygon. Concave has at least one diagonal with points outside the polygon. So concave is sort of this converse idea. It does have diagonals outside the polygon. So this is the shape that they're doing. And if I connect two vertices that are not adjacent, like right here from P to Q, that is a diagonal, and it happens to be outside of the rest of the shape. So we just label that concave. It's still a polygon, it's just a concave polygon. Most of the rest of the class will be dealing with just convex polygons. Now, we have some more special names for these guys. We have equilateral polygons. Just like we classified the triangles based on their sides. Do you remember the names for the sides of the polygons? Sides of the triangles? Yeah, let me review right here. Triangles, if we look at their sides, we had the names equilateral, isosceles, scalene. This was 3 equal sides, 2 equal sides, no equal sides. So just like for triangles, we can talk about equilateral polygons. So equilateral is this special case of triangles where all 3 sides were congruent. Guess what? Equilateral polygon means all sides are congruent. Then for triangles, we classified them by angles. What were the names of the triangles by angles? Right, meaning one right angle. Acute, meaning all less than 90. This was one equal to 90. Obtuse, one greater than 90. And what was that last one? Equiangular, the one you don't hear about very much. And that means they're all congruent. Hey, look, equiangular, equiangular. Equiangular polygons have all angles congruent. And a regular polygon is the most special case where you have both all sides and all angles congruent. Okay, let's practice. What do we have here? How many sides does it have? 12. So you could call it a dodecagon. Now, it says, draw a diagonal connecting 2 adjacent points of the star. Well, that's sort of a typo. If we just think about the points, then the adjacent pointy points are right there. Oops. Hey, that's a diagonal. And is it inside or outside of the star? It's outside. So is that concave or was that convex? Concave. How about Polygon AngleSum? Hey, let's talk about a decagon. How many sides does a decagon have? 10. So n is n. N is 10. Now, let's use the Polygon AngleSum theorem. Oops, sorry. AngleSum theorem, which was the first thing we talked about. N minus 2 times 180. Well, n in this case will be 10. So 10 take away 2 times 180. We're substituting the 10 for n. Then we'll simplify with a subtraction. And then 8 times 180, of course, is 1,440. Let's continue. Number 3. Use the Polygon AngleSum theorem to find out something that we're missing. Do you see, zoomed in right here and right here, this arc with the little hatch mark in it means they're congruent. Great. So let's zoom back out. Here we go. The figure has 4 sides, so n would be 4. Now, if we add up all of these interior angles, and they do mean the interior ones, here and here and here and here, then we'll get n minus 2 times 180. Well, that was the Polygon AngleSum theorem. Now, we know some of these angles. What's the measure of angle z? That guy. Hey, it's a little square. I know what that means. It means it's 90. And let's see, angle w. Oh, I know that one too. 100. So, on this side, I've got n, that was 4. Take away 2, that's 2. 2 times 180 is 360. So now I get to do some substitution. So now I've got x and y equals 190. And on the other side of the equal sign, I've got 360. Let me that was the simplification. Now I'm going to subtract 190 from each side, and I'm left with 170. So now all I've got is these two angles add up to 170. Well, let's see. If I know that y is congruent to x, then every time I see a y, I can write x. That was substitution. So I see a y, I'm going to write x. And this is actually saying the measure of angle x, but I think you know what I mean. So that's still 170. So now I've got two of these measure of angle x's that equal 170. Oops, fill in this blank, measure of angle x for measure of angle y. And then I get to divide each side by 2, and I'm left with the measure of angle x equals 85. That was a lot of steps for something that you probably could go through pretty quickly in your head. So just so you know, those were all of the right things to have on your page for that. Last page. Right. So let's apply the theorem 3-15, which is that the exterior angles always add up to 360. So we've got a regular hexagon that is inscribed in a rectangle. Have you seen that word inscribed? It means that you've got two things. Here's a circle, here's a triangle. The triangle is inscribed because it's inside the thing that we're comparing. So triangle, inscribed. Now, watch this. Here's a triangle. What if I draw a circle around it? Well, then I could say that the circle is circumscribed. Because now I'm talking about the thing that's on the outside. So it's the same picture, but depending on the thing that I'm talking about, I get to change my vocabulary. So here, it's the triangle that's inscribed inside something else. So here we go, hexagon inscribed inside something else. Now, the hexagon is regular, so all of its angles are congruent. I know, it doesn't look like a regular hexagon, but trust me, it is. So all the angles are congruent. And an exterior angle in the, an exterior angle is the supplement of a polygon's angle because they're adjacent angles that form a straight angle. What did that mean? Oh, I've got this side that I've extended, and this exterior angle is a supplement to the polygon's interior angle. So polygon angle was the red one. The supplement is the exterior angle that I'm talking about here. And because they're adjacent that form a straight angle, that's the definition of supplementary. And now, because supplements of congruent angles are congruent, do you remember where we learned that one? All of the angles marked angle 1 have equal measures. So the idea was this angle congruent to this angle, 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 because they said it is a regular hexagon. Now, every time I look at one of those intersections, I've got something like this. Here was that interior angle that's congruent to all the other green ones, and I've got an exterior angle every time. I add these up, I get 180, which is the definition of supplementary. So as I went around, all these smaller angles that are on the exterior, those were all marked 1, and those all added up to 180. And I think we're going to come back and talk about angle 2 in just a second. Now then, let's go down to the quick check. Classify the polygons by its sides. You try this. Six sides, so it's a hexagon. And concave or convex? Yes, convex. How many sides here? Ocho. So it's an octagon. Sorry. And if I connected this side, this corner, this vertex to this vertex, the diagonal was on the outside. So it's concave. Now let's find the sum of the measures of the angles in a 13gon. Hey, we have a formula for that. N minus 2 times 180. What's the n for? N is 13. So now I've got 13 take away 2 times 180. That's 11 times 180, which happens to be 1980. That was a good year. All right, now let's reverse our logic and see if we can figure out what the n is if we know the total number of degrees on the inside of the angle. That's this question, inside of the polygon. The sum of the measures of the angles of a given polygon is 720. Oh, got it. I could do that. 720. And the question is, how can you use the sum n minus 2 times 180 to find the number of sides? How can we use this? Well, hey, it's algebra. Get the variable alone on one side of the equal sign. Here's the answer to the question that we've been doing. What is the total number of degrees in the interiors of our polygon? And that will always be, parentheses, n minus 2 times 180. So let's do divide first, because I could have done distributive property, but then I would have some other stuff. So 720 divided by 180 is 4. And that equals the thing that I had left, n minus 2. Oh, let me add 2 to both sides. So the n was 6. What do we call that? Hexagon. So hexagons will always have 720 degrees inside of their interior. Now, okay, so we've got 720, here's the setup, n minus 2 times 180, n is 6. Okay, now, new question. Pentagon oh, sorry, I can't tap like that. ABCDE has 5 congruent angles. Find the measure of each angle. Oh, so they're all equal, but I need to know how much each one of them is. So pentagon. If I need to draw a pentagon, first I start with a pointy top, and then a flat bottom, and then I can connect the sides. There's a little hint. So now, each of these angles is congruent. Well, maybe if I knew how many they all add up to, that would help. Well, I can do my n minus 2 times 180, so that's 5, take away 2 times 180. Now I'm at 3 times 180, and that answer is 540. 540, that's the number of degrees in the entire pentagon. So if I added this, and this, and this, and this, and this, I get 540. And if they're all congruent, then I can divide by 5. Because if they're all the same, then each one will be 108. So if you had trouble with that, this is a very, very common kind of question that you must know this formula to be able to answer. This is all over SAT questions. So keep going. In the figure from example 4, find the measure of angle 1 by using the Polygon exterior angle sum theorem. So that was this whole, everything adds up to 360. So here's, oops, sorry, example 4. There it is right there. So we need to find what this measure of angle 1 would be. Now, let me clear this up a little bit. Go to red. All right, so we need to find this angle measurement. Well, it just so happens that it's formed by the interior angle of this hexagon, and angle 1 would actually be its supplement. So this whole thing would be 180. And I'm going to go with, since all of the angles in the exterior of a polygon add up to 360, how many of these little angle measurements do I really have? I have 6 of them. They did not note that here at these 2 corners. They only showed you the angle 1, this exterior angle, in 4 places. That's why this diagram, you might be saying, what? So they're only showing you these 4 angle 1s. Let me clear this up again. So I have a side, I have the other side extended. I have a side, I have the other side extended. I have a side, oops, I have a side, I've got another side extended. I have a side and one side extended. So now, here's 1, here's 2, here's 3, here's 4. I didn't do any extending of sides up here or here. So let me just do that real quick. Let's go red. So I'm just gonna, oops, red please. I'm just gonna extend this side, and here is my angle that happens to be congruent to that one. I'll extend this side and talk about this exterior angle. Happens to be congruent to this one. So I've got 6 of these angle 1 measurements. Here, 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 and here. Those were easy. But now I've just noted that I've got these 2 here. Guess what? They are the 6 exterior angles of this hexagon. For any n-gon, you will have n exterior angles. So if it's a hexagon, I'll have 6 exterior angles. Now, let me slide down to the bottom of the page and let's use that. So, with 6 exterior angles that are all congruent. Wait, how did I know they were all congruent? Because it says it's a regular hexagon. Definition of regular is angles congruent, sides congruent. So if all 6 exterior angles are all congruent, and Polygon exterior AngleSum theorem says they all add up to 360, then each one of them will be equal, so I can do 360 divided by 6, and those exterior angles each measure 60 degrees. 60 degrees. That's a little less than 90, isn't it? Hey, that looks about right. Let me wipe off the top of this one here. I'm talking about this angle. That looks like it's 60 degrees. That makes sense. 90 would have been a right angle. So 60 makes sense. And now find the measure of angle 2. Is angle 2 an exterior angle? Well, first let's find its measure. We were looking at this, and it is formed by one side of the hexagon and this other side that is not part of the hexagon at all. So there's your clue. This is not an exterior angle. In order to be exterior, you need to be formed by 2 sides. One side is sort of extended, one side stops. Angle 2 is not formed by 2 sides. Oops, big X through that. But we can figure this out. Do you see this little square? That means it's 90. We already figured out that 1 would be, angle 1 is 60 degrees. So if I use my triangle sum theorem, or I could even say n minus 2 times 180 happens to be 180 degrees inside a triangle, then 90 plus 60 is 150, leaving only 30 degrees for measure of angle 2. Whoops, too far. So measure of angle 2, angle 2 is 30, not an exterior angle. Whoops, spelled that wrong. There we go. Not an exterior angle because exterior angles are formed by sides of polygons. One side is extended past a vertex. Okay, great. Go on and try practice 3-5.